How to identify the zeros of the polynomial from the list of possible zeros. So far, we have focused our attention on a list of possible zeros, roots, of the polynomial. Now we are closer to the solution, but we still have a long path ahead, as not all the values listed are roots of the given polynomial. Indeed, from the previous tutorials, it is known that a fourth-degree polynomial, as in our example, may have 4 roots, zeros, at maximum. We have listed 40 possible values, so we have to reject most of them. There are 2 possible ways to identify all rational zeros of the polynomial p, x a. Substitute all possible zeros found earlier in the polynomial p, x, and check for which of these values we have p, x, equals 0, b. Use the synthetic division method for each possible zero and see which of them gives no remainder. The first method is faster for this process. Hence, we have the following shown on screen. Now that we identified the maximum possible number of 4 zeros, -1, 1, 2, and 3, we stop doing more calculations with the rest of numbers, as we already have the list of all zeros of the polynomial p, x. Indeed, the graph of this polynomial shows the 4 x-intercepts at the given zeros found. We have the following shown on screen. We can prove the results obtained using the synthetic division of polynomials method. Thus, writing at the upper row the numbers 2, -8, -2, 32, and -24, which correspond to the coefficients and the constant of the original polynomial, we obtain for the following schemes for the 4 zeros, -2, 1, 2, and 3, we have the following shown on screen. Now, let's see another scheme where the number on the left does not belong to the list of the polynomial roots. We expect to obtain a number different from 0 on the rightmost position of the last row, which represents the remainder of the division. Thus, for x equals 6, we have the following shown on screen. Thus, the remainder of p, x, and q, x, where q, x, equals x minus 6, is 960. Another advantage of the method described is that after having identified all zeros of the polynomial, we can write all possible forms of factorization for the given polynomial. The coefficients and the constant of the quotient polynomials appear in the last row. At this point, it is worth to state that the degree of the quotient polynomial is 1 less than that of the original polynomial. Hence, in the specific case, the degree of all quotient polynomials is 3. All factorized forms of the polynomial p, x, equals 2x to the power of 4 minus 8x cubed minus 2x squared plus 32x minus 24 are shown. A. Considering the root x equals -2 of the polynomial p, x, we obtain the following factorization shown on screen. It is better to have the polynomial factorized further if possible. In our case, it is easy to see that all terms on the second expression are multiples of 2. Hence, we have the following shown on screen. B. Considering the root x equals 1 of the polynomial p, x, we obtain the following factorization. We have the following shown on screen. Again, we can factorize further the second expression by sending out the common factor 2. Hence, we have the following shown on screen. C. Considering the root x equals 2 of the polynomial p, x, we obtain the following factorization. We have the following shown on screen. Again, we can factorize further the second expression by sending out the common factor 2. Hence, we have the following shown on screen. D. Considering the root x equals 3 of the polynomial p, x, we obtain the following factorization. We have the following shown on screen. Again, we can factorize further the second expression by sending out the common factor 2. Hence, we have the following shown on screen. That is all for lesson 11.3.4. To continue this tutorial, please watch 11.3.5, How to solve polynomial equations. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.